Are you there? Deborah, real quick.
Yes, dear.
Oh, I've asked a question. What is a conductor?
It's a device that stores electrical.
I said, what is a conductor? It's not a device. Inshira, are you there? Okay, a conductor is any material that allows the flow of current or charges. Deborah. So it's a material that allows the flow of current. All right. Okay, are you there? Deborah, are you there?
Yes, please.
So it's a material that allows the flow of current. Okay. Now, what does a conductor has differently from an insulator? Insulator, on the other hand, does not allow currents or charges to flow through them, right? So if you take an example of a conductor, let's pick aluminium. Aluminium. What is the atomic number of aluminium? What's the atomic number of aluminium?
13.
13. If you draw the electronic configuration, two electrons here, 8 electrons at the second shell, and 3 electrons within the valence shell, plus 11 neutrons. Now, what happens is that the nucleus, which is positively charged, okay, because it has protons, attracts these electrons. But usually what happens is that because there are a lot of electrons within that inner field shells or orbitals, so the K and L shell are the inner field orbitals or electrons. So the protons attract the electrons. Now, these inner field electrons shield the outer or the valence electrons. So these ones receive the attraction, meaning the attraction experienced by the electrons at the last shell would be very, very small. It is like similar to having a lot of people standing around a source of fire. So if you have a lot of people, okay, around source of fire, and there are about 2-3 people at the back, the effect of heat they would experience will be lesser because a lot of people are okay around would shield them. Please, are you okay? Are you okay?
Yes.
Deborah and Kay, are you okay?
Yes, please.
So in conductors, the inner field electrons shield the outer electrons. So they receive the attraction, and so the attraction received by the electrons at the valence shell, very, very, very small. And because of that, the valence electrons are less attracted to the nucleus. because of the inner field electrons. Okay, because of the inner field electrons, the attraction experienced by the outer electrons by the nucleus is very less. And so all metals, all conductors have this kind of electronic configuration. All copper, iron, zinc, when you draw their electronic configuration, we have a lot of electrons within the inner field shells. Okay, and so the effect of the attraction by the protons and the valence electrons very, very less. And all the electrons have this. And so because of that, we say conductors have free electrons in their valence shell. Because of the lesser attraction of electrons, let me say valence electrons by the protons within the nucleus. Conductors are said to have free electrons. Actually, free and few electrons. Free and few electrons at the valence shell. The valence shell is the last shell. Okay, so when we say electrons have free, conductors have free electrons at the valence shell, this is what it means. Because of the inner field electrons, they shield the valence electrons from the attractive force of the nucleus or of the protons. K and Debbie, are you okay?
Yes,
Yes, sir.
All right. So if a material had this, then the chances that the electrons, the valence electrons, can move to create current is high. That is why we say that current electricity is only talked about for conductors, because conductors only have these free electrons or valence electrons. All right. Now, current, when we talk of current, when the valence electrons move, then we talk about electric current. I'll come to that. So, if this is a conductor, a wire, the conductor naturally has free electrons, or which we are represented as here, charges. Okay, and at room temperature, these electrons are randomly within the conductor. Now, we want something to cause them to move. Okay, so we are looking for something which will cause the electrons to move. And Newton is saying that, okay, whenever there is an external force or a net force, it causes acceleration of a body. Okay, so we are looking for an external force which will cause these free electrons to move, because when they move, they create current. And so what do? We connect the conductor to an EMF, a source of EMF, plus or minus. This is a source of EMF. And the source of EMF creates the external field, which we technically call as electric field. So by connecting a source of EMF and an external force, known as an electric field is produced within the conductor. What is the source of EMF? EMF is electromotive force. Any force or any source which would force electrons to move, motive. Okay. What are these sources? Sources of EMF can be battery is one. Don't forget battery, we have dry cells, wet cells, and secondary cells. So the laboratory battery with EMF of 1.5 volts, car battery, and all that are sources of EMF. Then we can have generators. Generator, we can talk about the generator we use in our homes, and then our hydroelectric power station is also a generator. Then we can talk about dynamo, etc. Oh, these are EMF or sources that produce EMF or electromotive force. Okay, so if you have done electricity experiment, anytime we want to create a circuit in the lab, we have a battery. Then we connect the battery to conductors. And when the circuit, if this is a bulb, when the circuit is closed, when you have a closed circuit, this bulb will brighten or light up. Please, are we okay?
Yes, sir.
Are we fine? If you have any question, Deborah and Kay, if you have any question, ask. Debbie, are you there?
Yes, please.
So let's briefly talk about conditions necessary for current to flow. Conditions necessary for the flow of current. What and what must be in place for current to flow? One, there should be a source of EMF. And I've given you some examples of the sources. Battery, generator, dynamo, etc. Two, the battery must have, or the source of EMF must have a potential difference. A potential difference. When we talk about potential difference, we are talking about any 2 points that exist in an electric field. When you have the source, okay, when you have a source of EMF, electric field, F, which is equal to the charge times the electric field intensity. That's the electric force. Electric force F will be created. Now, whenever electric force exists within the wire, you have what we call electric field. Okay, so whenever you pick, if you have an electric field within a conductor and you pick any 2 points, the difference between these 2 points is what we call as the potential difference, which is measured by a voltmeter. And so for current to flow, there must be a source of EMF, and the source of EMF must have a potential difference. That is why the battery has one end labeled as plus and one end labeled as minus. The plus and minus is the potential difference. Another example of potential difference or gradient is that if you have a pipeline, assuming this is a pipeline, when the level of the line is just straight and you are channeling water through the pipe, the water would flow slowly. But when there is a gradient like this, if there is a gradient, one side up and one side low, the water flows with a greater speed. Please, are you with me? And so in this scenario, the upper part creates a higher potential, the lower part creates a lower potential. And water would flow easily when there is a potential difference, higher potential and then a lower potential. Another example of a potential gradient is, heat energy always flow from a higher temperature to a lower temperature. The difference between higher temperature and then lower temperature creates the difference, the potential difference. So current would also flow when there is a potential difference. When the potential of the two of the wires is the same, current will never flow. That is, and this explains the reason why on a high tension wires, when a bird perches on a single wire, the bird will not be electrocuted. But as the bird stands on a single wire, when it moves and then the wings touches another wire, the bird will be killed because perching on one wire and touching another wire would create a potential difference. Whenever there is a potential difference, current flows. When there is no potential difference, current will never flow. Please, Kay and Debbie, are you okay?
Yes, sir.
Yes, please.
So, the conditions are that one, there must be a source of EMF, and the source of EMF must create a potential difference. Then two, there must be a conductor because current flows only in a conductor. When there is no conductor, no current flows. And three, there must be a closed circuit. So these are the conditions necessary for current to flow. There must be a source of EMF. The source of EMF must also usually has the potential difference or creates the potential difference. There must be a conductor, and then there must be a closed circuit, meaning when any of these three aspect is missing, current will never flow. Any question? Any question? Hey, Deborah, today you don't ask questions. You of all people.
Steady, I don't have any question.
Hey, so
Yes,
Deborah, my question for you and Kay is that I'm coming. Why is it that when a bird perches on a single wire, it doesn't get electrocuted? Why?
Steady, please. You said it's because when it's on a single wire, there is no potential difference. And then the only way there will be flow of electricity or current is when there's potential difference.
Okay. Kay, I'm sure you would have said the same thing.
Yes, sir.
Okay, so all right. Now let's go into what is current. What is current? Or what is current electricity? So this is a conductor. A conductor has 3 electrons. At ordinary temperature, at room temperature, they are immobile, but they are free. They are looking for something to force them. And so when you connect a source of EMF and there is a potential difference, force acts on them and they drift or move with a certain velocity within the conductor. Now, anything that moves creates a current. And so water moves. And so we have water currents. Wind moves. We have wind current. Anything that moves creates a current. So you can't just say current. You must talk about current electricity so that it distinguishes it from water current and wind current. Okay, because anything that moves creates current. We have water current, we have wind current. So when you are talking about moving charges, then talk about current electricity. Now, by virtue of the source of EMF applied, the charges are moving. If you put a gauge over here across the conductor, the gauge is to measure the quantity of charges. This is pushing the charges because there is an electric field. The electric field is causing acceleration of the charges. So if you put a gauge here to measure the quantity of charges that are crossing this within a given time, okay, so a measure of the number of charges flowing divided by a given time is what we call as electric current. And so we define electric current as the flow of charges within a given time t. So electric current is represented by the letter I, and this is Q charges represented by Q divided by time. So current is equal to charge over time. That is electric current. So you can't just say current, but here you must talk about electric current, because when you talk about electric current, what it means is that you are looking at flow of charges within a given time t. Now, the basic unit of electric current, I, is the SI unit of charge is Coulomb. SI unit of time, second. So actually, the basic unit of current is Coulomb per second. Coulomb per second. But it was handed to a famous physicist who was very instrumental in current, electricity, ampere. And so the SI unit of electric current, SI unit of electric current became ampere. Ampere, shortened as capital E. But the actual derived, the basic or the derived unit is Coulomb per second. Coulomb per second. SI unit ampere. 1 ampere of electric current. 1 amp of electric current is when 1 coulomb of charge, electric charge, flows within a second. So 1 ampere is 1 coulomb over 1 second. 1 ampere is equal to 1 coulomb per 1 second. Are we okay?
Yes, sir.
So current is actually the flow of charges within a given time, but we often peg it for 1 second. So 1 ampere of electric current is 1 coulomb of charge over 1 coulomb of charge flow within 1 second. The device or the instrument used for measuring electric current is the ammeter. Okay, so the ammeter is used in measuring electric current. Ammeter is used in measuring electric current. So the ammeter. Debbie, are you there?
Yes, please.
Or use is a device used for the measurement of electric current. In a circuit, an ammeter is always connected in series. So an ammeter is always connected in series. The reason is that, as I told you, if this is a source of EMF, battery, and we are looking for the current flow, the charge, the movement of the charge which creates the current, okay? The charges move within the conductor. So if you want to measure how the number of charges crossing, then you must break the circuit. You must break the circuit and put in their instrument. So when the instrument is here, it will be able to detect the charges crossing from here to this point. Okay, so you must break the circuit to put in the device. When you break the circuit and then you put in the device, you have connected the device in series. So ammeters must always be connected in series within a circuit. Kay and Debbie, are you fine?
Yes, sir.
Yes.
All right, so let's look at Ohm's law. Ohm's law. Ohm's law. Ohm's law. What does it say? What is Ohm's law? If I have a circuit and there is current flow, meaning for current to flow, okay, tell me one of the conditions I need to have for current to flow. What must be in place?
There must be an EMF, and the EMF must have a potential difference.
Thank you. So I have a source of EMF, battery. So positive, negative. The positive and negative polarity or poles of the battery creates the potential difference. And then, Debbie, what is the other condition?
There should be a conductor.
So I must have a conductor. And what must be the other condition, K?
The circuit must be closed.
So I have a closed circuit, meaning that is why in a circuit, if I have a key, which is a switch, when the switch is open, no current flow. For current to flow, we must close the key. Ohms, my good friend Ohms is saying that in a closed circuit, when temperature and other physical conditions are constant, so in a closed circuit, when temperature and other physical conditions are constant. The potential difference in a metallic conductor is directly proportional to the current flow. All that Ohms is saying is that if you have a closed circuit and you keep the temperature of the metallic conductors constant, if T is constant, temperature of the conductor does not vary. Whenever you pick any 2 points, okay, in a metallic conductor, maybe this point and this point, and I want to measure the potential difference across these 2 points A, B in the metallic conductor. And how do I measure? I can measure the potential difference by connecting a voltmeter to the chosen point. V. So I'm choosing any 2 points within the metallic conductor, this and this. Okay. All that Ohms is saying, when the temperature of the metallic of the circuit or the conductor is constant, the potential difference V across the metallic conductor is directly proportional to the current flow I. And this is what we call as Ohm's law. In a closed circuit, of course, the circuit must be closed, because if the circuit is not closed, what happens? If the circuit is not closed, what happens? Yes.
Current will not flow.
Current will not flow. So in a closed circuit, when temperature and other physical conditions are constant, the potential difference in the metallic conductor is directly proportional to the current flow. My big question is that, what is a potential difference? I've talked about it, but I'll ask again. Why must temperature be constant? And what we mean by why metallic conductor? Why metallic conductor? And what do we mean by direct proportionality? So these are the questions I have for you. The first question is that, what is a potential difference? What is a potential difference? Anybody? What is a potential difference? I said it. Whenever you have a metallic conductor and there is a source of EMF, the moment you connect a source of EMF, we have electric field created within the metallic conductor. So when there is an electric field, when you pick any 2 points within the electric field, the direction of the electric field, those 2 points, the difference between, okay, the difference in terms of potential between the 2 points is what we call as potential difference. So potential difference is the difference between any 2 points that exists in an electric field. So to talk about potential difference, there must be an electric field. Are we okay? Any choosing points, that dwells in an electric field is what we technically call as potential difference. My next question is that why must temperature be kept constant for the law to hold? Why must temperature be kept constant? Yes, Debbie.
So yeah, please, I think when like you increase temperature, the number of charges or electrons in the conductor will gain sort of energy and they'll be moving.
Anyway, you have made your point. Okay, it's not completely in line, but it's also good. Okay, what do you also think? Why must we keep the same constant? Why must temperature be kept constant? Okay, do you have any idea?
I think it must be kept constant because if the temperature should increase, then the current would also increase, and because of that, the ohms law will not stand because there will be more current than the potential difference.
All right, so you have also given something, but okay, so the truth, as you all said, change in temperature would affect the current. Meanwhile, for the law to hold, we expect a steady current flow. We shouldn't have a situation where the charge flow is either increasing or decreasing. It must be steady charge flow, and that will give us a constant current. Now, when temperature changes, it will affect the rate at which the charges are flowing, and so would affect the current. Later you will understand, but that is the reason for which temperature must be kept constant. And then we are talking about Ohm's law. We are only applying Ohm's law to metallic conductors. Why? We are only applying Ohm's law to metallic conductors. Why? Can you brainstorm something and tell us why? And K, can you share your opinion? We are just sharing views. Why are we talking about only metallic conductors?
I think metallic conductors are the only like material that will like conduct electricity because it has the localized electrons.
Oh, you sweet terms, yo. K, do you have anything to add? Okay. You see, electrolytes, such as salt water or ionized water, also allows charges to flow. So electrolytes such as sulfuric acid, nitric acid, okay, these are solvents that also allow charges to flow, but they do not obey Ohm's law. And so, because even though they are also conductors, they do not obey Ohm's law. For them, V is not directly proportional to I. And so whenever you are talking about Ohm's law, you must limit it to metals or conductors that obey Ohm's law. The voltage drop across a section of the length of the conductor is directly proportional to the current flow. So that is why for Ohm's law, we are always talking about metallic conductors, because we have other conductors, but they do not obey Ohm's law. Please, is that understood?
Yes, sir.
Yes.
Okay. Then, when we say two quantities relate in such a way that they are directly proportional, okay, what do we mean? When two quantities are related in such a way that they are directly proportional to each other, what does it mean, K?
It means that increase in one quantity results in increase in the other quantity.
Perfect. Perfect. So, V, for Ohm's law, V is directly proportional to I, meaning that an increase in the rate at which charges flow, current, affects, also increases the voltage drop across the metallic conductor. And V is equal to a constant of proportionality times I. This constant of proportionality K is what we call as the resistance of the conductor. So V is equal to I times R. This is what we are calling as Ohm's law. In fact, materials that obey Ohm's law, if you obey Ohm's law, then the potential difference across any section of the material must be directly proportional to the current flow. And these materials that obey Ohm's law are known as ohmic conductors. So materials that obey Ohm's law are known as ohmic conductors. So ohmic conductors are conductors or materials that obey Ohm's law. Those materials that do not obey Ohm's law, such as tungsten filaments, semiconductors, electrolytes, these are called non-ohmic conductors. And in fact, ohmic conductors are generally all metals. All metals obey Ohm's law. So when we talk of all metals, we can talk about aluminum, we can talk about copper, we can talk about zinc, we can talk about iron, basically all metals. The non-ohmic conductors do not obey Ohm's law. Example, electrolytes, tungsten filament, semiconductor diodes, etc. Now, when materials obey Ohm's law for ohmic conductors, when you plot voltage against current, voltage or potential difference V against current, I, you have a straight line. You have a straight line. The slope of this straight line is equal to that constant slope, which is the change in voltage over the change in current, is equal to the resistance. So metallic conductors or ohmic conductors, when you plot their potential difference against current, is a straight line. Ohmic non-ohmic conductors, when you plot V against I, you have a curvy something like this, or sometimes logologic. So that wouldn't give you a straight line, but for ohmic conductors, it's a straight line. All right. Please, any question? So we've understood what we mean by current. We've also understood potential difference or voltage drop. Now let's look at resistance. What is resistance? What is resistance?
Mr. Dear.
What is resistance?
Mr. Dear, I think resistance, like the ability of like the resistor to resist like the flow of electric current or control the amount of electric current.
Okay, what is resistance? What do you also think?
I think that resistance is the opposition of flow of current in a circuit or conductor.
Okay. All right. So you are all, in fact, giving such a wonderful contribution. So as you all said, resistance is the opposition to the flow of current. But by what? By what? What provides the opposition to the flow of current? Okay. What provides the opposition to the flow of current? Okay.
I would say impurities in the conductor.
Is the conductor. Okay. So within the circuit, Deborah, are you there?
Yes, please.
Within the circuit, the conductor provides that opposition to the flow of current. In fact, different conductors offer different opposition to the flow of current, meaning different conductors provide different resistance. In fact, among all the metals, copper provides the less resistance. And we say that copper is the most conductive metal. And electrical wiring, if you are going to buy copper cables, it's very, very, very expensive because copper wires are highly conductive, meaning they are less resistive. They will resist the flow of current less and allow current to flow the more. The lesser the resistance, the higher its conductivity. So its ability to allow charges to flow and a friend conductivity. Copper is a highly conductive metal. Copper offers less resistance. Aluminium is another conductor. Its resistance level is greater than what copper offers. Iron. So different metals offer different resistance or opposition to the flow of current. So the opposition to the flow of current is provided by the material. Conductors have specific resistance or opposition to the flow of current. Please, I hope that's okay. If the material offers less resistance, you're saying the flow of current is high. Now, what actually brings about resistance? We've understood that resistance is the opposition to the flow of current. But what causes it? What causes it within the material?
Mr. Diabs, I think opposite charges.
Opposite charges.
Yes, please.
What do you mean by opposite charges? Gabby, what do you mean by opposite charges? Can you explain further?
Mr. Dia, I think maybe if across the conductor, the electric current flowing is negatively charged, and the one like opposing it is also, hey God, Mr. Dia, I don't know how to explain.
So resistance is offered by the material or the conductor. Different conductors offer different resistance or opposition. Now, Radia, within a conductor, if this is a wire, for current to flow, the circuit must be closed. We need to have a source of EMF. Okay, are you there?
Yes.
This is the wire. The four square is the wire. The moment you connect a source of EMF, you have introduced an electric field or electric force, F. The electric field would cause the charges to drift, move with a certain velocity. But the funny thing is that whenever for a wire, whenever you connect a source of EMF, the moment the source of EMF imposes a force in the circuit, the wire begins to heat up because of the force. This is what it means. The charges are initially stationary. If there is a force pushing us to move within the volume of the cable, there is a force. Okay, when there is a force, particles within the conductor would vibrate. Will vibrate because there's a force pushing them. Okay, kinetic theory, HSA, average kinetic energy is directly proportional to what? Average kinetic energy is directly proportional to absolute temperature. So for molecules or particles, average kinetic energy of the molecules is directly proportional to absolute temperature. What it simply means is that within a system, when you have the kinetic energy of the particles increasing, it also increases the absolute temperature. So the moment you introduce a source of EMF, which creates a force or electric force or electric field, because it will cause the charges to also move, it increases the temperature of the conductor. Now, when the temperature is not constant and it is varying, you see, when the temperature varies by raising or decreasing, it means the kinetic energy would also be greater and then decrease with time. So if the temperature doesn't stay constant, it will affect the current flow. Please, are you with me? Are you with me? Hello, are you following?
Yes, sir.
Deborah, are you gone? So, what happens is that the moment your line is breaking, the moment the field is introduced, okay, because particles begin to vibrate as a result of the force, then the charges, we have particles, atoms of the conductor. So these are atoms. They are vibrating. Around each atom, there is a free electrons that are being pushed. So let's indicate this to be 1, 2, 3. Every atom has a mobile electron, a free electron that can be pushed. So the force is pushing these charges, which are electrons, to move. Meanwhile, this sense, the atoms are also vibrating because the atoms are particles. Around the atoms, we have the charges, which are electrons. They are vibrating because of the introduction of the electric field. Once they are vibrating, the force which has to act on the electrons to move, the chances that the vibrating atom can knock off an electron is high. Okay, let's take myself to be an atom. Around me, I have an electron and I'm vibrating. When I vibrate so much, and electrons must flow in a particular direction, because I'm vibrating because of the field, external field, the chances that I can knock off a moving charge, whose movement creates a current, is high. So when I'm vibrating, another atom is vibrating, another atom is vibrating. Because they are vibrating, they can knock off electrons and then reduce the flow, the consistency of the flow of the charges. Is that okay? And that brings about the resistance. Hello, are we okay? Are we okay?
Yes.
Yes.
Give me a minute, I'm coming. Okay, so resistance in a circuit is actually caused by that when the field is introduced, there's a vibration of the atoms, okay, or the particles of the conductor. And these vibrating particles knocks off a free-flowing electron. The free-flowing electrons or charges create current. Because the particles are vibrating, they can knock off the free-flowing charges or electrons, which create current. So the more the particles vibrate, the more electrons or charges are knocked off from their direction. And once it is like, I must have 10 particles to flow to give me current. Now, as a result of introduction of the external field, the 10 particles have reduced to maybe 8. So the current flow will drop as a result of, and this is resistance. But different conductors does it differently. That is why different conductors have different specific resistance they offer to the flow of current. Now, the reason why when temperature is increased, it affects current flow is that, as I said, average kinetic energy is directly proportional to absolute temperature. So when you increase temperature, you are increasing, it is equal to an increase in the kinetic energy of atoms or molecules. Increase in kinetic energy of atoms. So if kinetic energy of atoms is increased, they will vibrate the more at their mean position. If they are vibrating the more, they will knock off a lot of electrons which must flow to give you current. Hence, increasing temperature would, when we increase temperature, please, will it increase resistance or decrease resistance? Hello?
Increase resistance.
So good. So when we increase temperature, it would increase resistance. And when resistance increases, what happens? When resistance increases, what happens?
Current is unable to flow. Like
Conductivity is also reduced, or flow of current is reduced. That is all. That is why in Ohm's law, there must be a constant temperature. Because when temperature is not constant, either current flow, okay, would increase or decrease, but we must have a steady current flow. Okay, is that okay?
Yes, sir.
Please, if you have any question, ask. If you have any question, ask. So that is resistance. Okay, the SI unit of resistance is actually ohm. Ohm.
Mr. Dia.
Hello, Arabia.
Mr. Dia, please, I wanted to ask something. When it comes to current, does it have a particular charge, let's say negative or positive?
You see, a flow of charge, it can be positive, it can be negative. Okay, but because we are saying charge flow is about the electrons of a material, we are always limiting it to a negative charge because of electrons. But it's about the flow of charge. When the charge is positive or negative, and it is not stationary, but it's in motion, okay, it's being a charge and it's being in motion brings about electric current. Are you okay?
Yes, please.
All right. So different materials or conductors offer specific resistance to the flow of current. This specific resistance they offer is what we term as resistivity. So resistivity is the resistivity of a conductor. Resistivity of a conductor is the specific resistance conductors or let me use materials, and here we are talking about metallic conductors. Materials offer to the flow of current. So resistance SI unit ohm. Now let's look at factors, that physical factors or factors that affects the resistance or factors that affect resistance. That affect resistance. Resistance. Meaning certain factors can either increase or decrease the magnitude of the opposition
Mr.
of
Dio,
hello.
please, the resistivity. I can't see the part that says is the specific resistance some
Is a specific resistance materials offer to the flow of current. So different conductors have different resistivity. Okay. Different
yes,
conductors have different resistivity. Factors that affect resistance. We've talked about temperature. Yes. Increase in temperature, of course, increases resistance in a metallic conductor. So let's, aside temperature, let's talk about the physical factors. Resistance R is directly proportional to the length of the metallic conductor. So we are saying that R is directly proportional to L. The greater the length of the metallic conductor, the greater is the resistance. Can somebody explain why? Can somebody tell me why? Why is it that if we increase the length of the metallic conductor, we are increasing resistance?
So I think it's because if we should increase the length, then it means that where the points between the points of the conductor have increased, meaning the current will have to flow over a greater distance.
Yes, and when it flows over a greater distance, what is the problem? Okay, what is the problem when it has to flow through a greater distance?
Mr. Dia.
Okay, let Deborah come in.
Mr. Dia, please, if it's traveling a longer distance, you require much energy.
Okay. Hey, do you have anything to add?
So I would say that the number of charges that would go over the distance, there would be more distance between the charges as compared to if it were shorter. Because if it's longer, then the charges won't be able to flow at the same rate.
Okay, you've all shared your view. So if 1 meter length of a wire has X resistance, when you join it with another 1 meter, the total resistance becomes 2X. This resistance plus this resistance. If you are to add another 1 meter, it will be 3X. The reason is that I just told you that resistance is as a result of the knocking off of charges as a result of vibrating atoms. So when the EMF is set up within the conductor, there is electric field. The electric field would increase temperature. When temperature is increased, okay, the particles will vibrate. When they are vibrating, the chances that the electrons can be knocked off, because as will be a wabodam or moving about, you can be knocked off. Okay. Now, as you add more, as you increase the length, you are adding more atoms. 1 meter has X volume of atoms. If you bring another 1 meter, you are adding the same number of atoms to the first one. So when you set up a field, they will all vibrate, and the chances that they would, as it travels on and on from the beginning point to the end, it would experience more knocking of electrons is higher. So the moment you are increasing atoms, and they will all oppose the flow of charges. So the greater the length of the conductor, the greater will be the resistance. Please, are you okay? Debbie, are you fine?
Mr. Bia.
I hope you are not sleeping.
Hey, no.
R is also inversely proportional to the cross-sectional area of the conductor. Resistance is also inversely proportional to the cross-sectional area of the conductor, meaning an increase in the cross-sectional area would cause a decrease in the resistance. A decrease in the cross-sectional area would also cause an increase in the resistance. Why? Tell me why. Why is resistance inversely proportional to cross-sectional area? And now, Kwame, you break the ice. Why is R inversely proportional to A? Okay, any idea? Hey, okay, are you there? Or you are also asleep?
No, I'm not asleep.
Why is resistance inversely proportional to cross-sectional area? So you are thinking about it. Okay, Deborah.
Mr. Bia. Because I think when the surface area is increased, the pressure for the vibration of the atoms will decrease because they will be more apart. So when they are connected to the EMF and they are moving, it won't hit or clash each other because of the large surface area. So it will reduce the resistance.
3/10.
Hey,
Because using pressure, you are putting pressure on yourself. Okay, what do you also say? Why is R inversely proportional to A? Okay, are you there?
Yes, I'm here.
Hey, I'm waiting for you. What do you also say?
But I'll say that if the cross-sectional area increases, then it means that more of the electrons will be free to move. So the current would increase and then the resistivity would decrease.
Okay, so that's the point. Deborah, when we increase the cross-sectional area, we have increased, it's like on a highway, you have X number of cars along the road, along a single lane. When you increase the number of roads, there are greater space for the cars to maneuver, so traffic will be less. So by increasing, okay, yes, particles, atoms will be vibrating, but there will be space for the free-flowing electrons to pass. So when they are passing, even though charges, atoms can be vibrating, but the chances that they will be knocked off is less compared to when the cross-sectional area is small. Debbie, are you okay?
yes, please.
So it's synonymous to highway. Single lane, more traffic. Double, triple lane, less traffic because there is wider space for vehicles to maneuver and move. So here the vehicles are the charges. All right. And so 3 factors that affect resistance, we've talked about length of the conductor, the cross-sectional area, and then the resistivity of a particular conductor. I said the resistivity is the specific resistance conductors or materials offer to the flow of current and temperature. So we've talked about 4. 1, length of conductor. 2, cross-sectional area. 3, resistivity of the material. And then 4, temperature. In fact, some of them are not physical. So when we bring together those physical ones, we have resistance directly proportional to L, inversely proportional to A. If we equate it, we have R is equal to a constant of proportionality K, L over A. This constant of proportionality is the resistivity, which is the specific resistance offered to the flow of current. So R is equal to K, which is rho. Resistivity is represented or has a symbol as rho as density, the symbol for density. And so when we put these actors together, we have R is equal to rho L over A. This is the factors on which resistance dwells on. These are physical factors, measurable factors. The other unseen factor is temperature. So an increase in length increases resistance. An increase in area decreases it. Please, are we okay? All right. Okay. So I think let's end today's session here. We have about 15 minutes left. So let's end here and then we'll continue. But I'll update the time. Okay, other students are bringing me their own free time. So I'll look at it and then polish our meeting days properly and then update you on the platform. Is that okay?
Yes, please.
All right. So this is where I end today's show. Please, good night to all of you. We shall communicate on the platform. All right. Bye-bye. I'm recording the video, so I'll send the video to you as well. Okay.
Yes, please.